This simulation represents a hydroelectric plant built entirely in Siemens TIA Portal. It demonstrates advanced PLC programming, HMI design, and real-world automation problem-solving, using multiple languages like ladder, function blocks, structured text, statement list, and sequential function chart. I developed a comprehensive system to manage modes, alarms, and process control. Initializing the project, we can see that we have a security window that will manage the users to do certain configurations on the system process. The project works on 5 different modes that we can see on the left of the screen on the SFC program file. And we can see that as fast as the start button is pressed, the program transitions out of the idle mode to warm up. And in this step, we are going to be watching a ladder file that is going to be waiting for certain conditions to be accomplished, and after certain time is going to be triggering on a one-shot block a bit that is going to be transition the program out of warm-up to stabilize. As you already have noticed, this program works triggering bits to transition out of the SFC file, and in this occasion we are going to be managing all the logic on an FBD file to transition out of stabilized mode. Now, working on exclusively STL, the program waits for the stop button to be pushed or for an alarm to happen to transition out to cooldown. Finally, on cooldown, we manage the simulation logic only with STL programming, though it could be any other, and by setting on and off the correct process devices, the process starts shutting down and will transit to idle mode when the temperature gets down to transitioning out setpoint mode. Now, going back to ladder language, an e-stop alarm is simulated, and an alarm screen pops up immediately. And since it works in accordance with holding circuit's logic, it allows the operator to silence or reset the alarm. Depending on the language that we have selected, a determined function block language will be energized. In this case, this function block controls the I/O device's logic, and if all devices are in auto mode, control bit will be activating and deactivating our devices. Changing to function block language, we can see that by pushing the HOA buttons, the state of the devices is changed. On the SEL language, we are going to be using the function of scaling, that depending on if it's a real or an int, it's going to make easier our sensor selectors scaling. On the same way, due to the nature of the STL language, a convert time function is used, all with the intention of being able of changing timers presets from the HMI. The project has the capacity of change the language without interrupt the process simulation. So depending on the language that is running, the blocks that are not on the language selected are going to stop receiving data from the simulation logic. This way, all the data is frozen when a language change is executed to be taken by the new language running. Now, let's talk about the HMI screen. The overview screen provides a live dynamic display of the process, showing key parameters like flow rates, power output, and device status. On the other hand, the setpoints configuration screen offers a drop-down list to navigate different setpoints and allows the operators to modify control setpoints directly from the HMI, with user-friendly scaling and input formats. The HOA screen allows us to select the mode of the digital devices and to select between manual or automatic control on the PID analog control. The trend screen also uses a drop-down list to navigate through the different devices and what it's controlling over the time. It also shows if the device and the magnitude are being controlled by a PID, and if so, what its set point is. Now, watching a commissioning screen is important to mention how the system works, and since the simulation logic is simulating a variable river flow, all the variables are going to depend on how this flow is managed, and according to the current mode, the output of the PID is going to be the percentage of the output of the device in question to control any specific parameter. For example, the baffle has two different PIDs configured and tuned, one for control the current and one for control the RPMs on the rotor speed, and the VFD pump has one PID to control the gallons per minute and other to control the temperature on the rotor bearings. As we can see, this trend shows when the mode changes and the VFD starts to take control over the temperature. The system also counts with 4 different data log tables that are going to be storage on different text files. This project demonstrates my skills in PLC programming, HMI design, and process automation. It's a proof to my ability to tackle complex challenges and deliver practical, industry-ready solutions. If you'd like to learn more or discuss how I can contribute to your team, feel free to reach out. Thank you for watching.